Hello class, welcome back to another section of our intensive calculus course. In this class, we are going to talk about limits of functions. If this is your first time visiting this class, don't forget to subscribe and also like as well. Watch this video to the end so that you understand every part of the video. And the limits of functions, we're going to look at the properties of limits, then we solve some examples I have here. First of all, when you say limits of functions, what are we talking about? Now, when you are having functions in calculus, when you are dealing with functions, functions will have a limit as you approach to certain numbers or certain values on our domain. So, assuming we have a graph, then we have a certain curve here where it's a function, and I have -1, -2, then I also have 1, I have 2. I'll ask myself, what will be the limit of this function? How will this function limit me as I approach -2? So this is the x, this is what I'm talking about. This is the domain, and this will be the codomain or the range. This is what we put into the function to give us its reflection or its image. So as I approach this -2, what will be the limit of this function? So this is simply this point. To realize that as you are approaching -2, then the graph moves up, but right at the point of -2, this will be the maximum peak it will reach, and you just trace that to the y part, so that you say that the limit of this function as s is approaching a -2 gives us 2. Now, in every limit, we have, since on the number line we have positive and negative, or we have left side and right side. When I consider this -2 here, if I want to find the limit as s approaches -2, I have two ways of doing that. I can either approach this function from the right side, or I can approach this function from the left side. So if I am to extend this place, then I introduce -3, -4, and I am to come from this side. When I reach here, I will still reach the same limit. So in the definition of limit, we say that a limit has right side. So when I take limits, we write it this way: as x approaches, let's say 2 of the function f of x. So once I write this is the general notation of a limit. This is the total limit. Now we have the part limit, that is the right side limit and the left side limit. So if I want to use the right side, you say limits as s approaches 2, then you introduce plus here. That means you are talking about limit from the right. But if I write limits as x approaches 2 minus, meaning I'm approaching these two from the left. So that is how we denote limits. So when you see plus on the number here, then it means it is from the right. When you see minus, then it means it is from the left. So back to what you're talking about. So in all, when you have a continuous graph, when you say a continuous function, a smooth function like this, and normally when they give you polynomial functions, as you see smoothly here, we just put in the functional value. But when we are considering step functions and piecewise functions, then you introduce this right limit, left limit very well. So let's move straight to solving some of the problems I have here so that you understand what I'm saying very well. But before that, let's talk about the properties of limits here. So when you say limit has its own properties. So the first property I'll talk about is that when you find limits of x approaches any number, say x0, of a function f plus g of x. This means that you have two functions being added together. Then our resulting solution is going to be the limit of f of x alone, limits as x approaches x naught of f of x alone, then plus limits as x approaches x naught of g of x alone. So this is the first property. Then the second property, we're going to have limits as x approaches x naught of c, which is a constant, an arbitrary constant, multiplying the function f of x. Then our limit is going to be c multiplying the limit of the f of x alone as x approaches x naught. We don't include the constant. Then let's see the third one. The third one, you're going to have, if you have a limit of a rational function f of g of x, any two functions which are in quotients, then we simply find the limit of the first one over the limit of the second one. Then we come again, then if you have limits of any function to the power n, f of x to the power n as x approaches x naught, then your limit solution is going to be the limit of f of x as x approaches x naught all to the power n. So from here our solution is going to be ln, where L is our limit point. So finally, let's look at the last property here. So the last property is saying that if you have a limit of any function under the square root sign nth root f of x as x approaches x naught, then our solution is simply going to be the square root nth root of limits of f of x as x approaches x naught, and our solution is going to be the nth root of L. Meaning, if I've been given any function under the square root and you have to find a limit, we just don't include the square root. You put the square root out and you find the limit inside. That is the basic properties of limits. Now let's go forward solving the problems I have. So the first problem I'm going to solve with you is the first one. We have to find the limits of the function 2x squared minus 2x plus 2 as x approaches 2. If you have this expression to find the limit, from the properties, this is a constant, this is a constant. Then finally the last property, lest I forget, it is saying that the limit of any constant function. So let me put it here. The sixth property, if you have the limit of any constant function, let's say f of x equals 5, limit as x approaches any number x naught will give us 5 as our solution. So in general, if you want to find the limits of a constant function using c as an arbitrary constant, the solution will be c irrespective of the value of x you are approaching. So let's come back. Limit of x 2x squared minus 2x plus 2 as x approaches 2. So how do you find the limit here? We have to apply the properties of limits. That is, there are sum of functions here as well as we have the coefficients. So I'm going to get 2 open brackets limits of x squared as x approaches 2 alone plus, then I come here, this is minus, so minus 2 open brackets limits as x approaches 2 of x, then plus limits of 2 as x approaches 2. When I get this limits here, I'll just put the 2 to this. From the graph as I showed you, you just put 2 here to this x. That is, wherever you see x, you put 2 there. So I get 2 open brackets 2 squared minus 2 open brackets, I'll put 2 because here is x. I'll just put 2 there. Plus, and from the other property saying that the limit of any constant function is the same as the value I have here, so plus 2. And this is going to give me 2 times 2 squared, that will give me 8, minus 4, that will give me 4 plus 2, 6. And that is our limit. So if you draw this graph, if we draw this graph and we find the limits on the graph, you realize that at x equals 2, you get 6 as the limits on the graph. Let's go to the second example, and it's saying that limits as x minus 1 over s squared minus 1. Let me divide my working space. So if you have the limits of this as x approaches 1, you know from maths, when you get a denominator to be 0, it makes the whole rational function undefined. So we always do away with that. So how do we go by this? If I am to put 1 just here, I'll get 1 minus 1 over 1 minus 1, and that is going to give me 0 over 0, which is not allowed. So what I'm going to do is, I'm going to simplify this place. So I have x minus 1, and you know that if you have this difference of 2 squared, so x minus 1, x plus 1. Then after this, we'll cancel this, so that I get 1 over x plus 1. So at this point, wherever I see x, I put my 1 here, there, because I said as x approaches 1. So I'm going to get 1 over 1 plus 1, and that will give me 1 over 2 as my limits. Then I move to my third example I have here, and this is limits as s cubed plus 2s squared minus 1 all over 5 minus 3x as s approaches negative 2. So whenever they give you rational functions, first put the number, the limiting number, to the denominator to test if it will give you undefined. So if I put negative 2 here, I'm going to get 6 plus 5, 11, and it wouldn't affect, or it wouldn't give me an undefined solution. So this will be equal to, wherever you see x, you put negative 2 straight away. So negative 2 all cubed plus 2 open bracket negative 2 all squared minus 1 all over 5 minus 3 open bracket negative 2, and this is giving me negative 8. Here is 4 plus 8 minus 1 all over 5 plus 6, and this is going to give me negative 1 over 11 as my solution. Then I move to my fourth example. My fourth example is limits as f of x equals 4 approaches 2. So for this one, as I said from the properties, the limit as any constant function approaches any number is the same as the resulting value here, or the constant value. So this, our solution is simply 4. Now I have my final example, my sixth example. I have square roots s squared plus 9 minus 3 all over s squared as x approaches 0 limits. So first of all, as I said, rational functions, you are supposed to put the limiting value into the denominator, and once I put it here, you realize that I'm going to get undefined. So what does that mean? I have to find a way to do away with it. In the other example, I saw that I could simplify this and I'll cancel out, but here I can't do that. Now if you are having any expression with radical signs in it, it's best to use the conjugate. I believe you've done CERS in high school and also in elective maths in particular. So what you're going to do is, you take this function here, that is square roots s squared plus 9 minus 3 over s squared. Then I'm going to multiply. We assume that it is being multiplied by 1 here. So I'm going to multiply it by the conjugate. So I'm going to get square root s squared plus 9 plus 3. This is the conjugate. Here was minus. Here is going to be plus 3. All over square root s squared plus 9 then plus 3. You realize that when I cancel this and this, it still gives me 1 and have done nothing here. So let's see what we're going to get. So at this point, this will multiply this, and I'm going to get s squared plus 9. Seeing the square root will vanish. Then I'll multiply this by this positive 3. So I get plus 3 square root s squared plus 9. Then I'll multiply this negative 3 by this, and I'm going to get minus 3 square root of s squared plus 9. Then minus 3 times 3 minus 9. All over the denominator, I'm going to get s squared multiplying square root s squared plus 9 then plus 3s squared. So at this point I can see that this will cancel this simply. Then I'll be left with this 9 will also cancel this 9. So I'll be left with simply s squared over s squared multiplying. So let me factorize s squared here. So I get root of s squared plus 9 plus 3. So that this will cancel this, and I'll get 1 over the expression square root of s squared plus 9 then plus 3. At this point, wherever I see x, I put my 0 there. So I'm going to get 1 over the expression root of 0 plus 9 then plus 3, which is the same as 1 over root of 9 plus 3, which is equal to 1 over 3 plus 36. So these are the basic limit concepts. We just solved some basic limit properties, and in the next class we are going to tackle the right and the left limit of piecewise and stepwise function, which are a bit confusing. Don't miss that class. Thanks for watching. Don't forget to share to your friends.